he has been I hope that our students will be much more benefited from his rich experience and his background in this particular topic. So let us all invite Professor Minal Geosciences to start his experience through the technical talk.
Okay, so would you let me share my screen?
I have just a minute.
Yeah, I think I can.
I have given the sharing options. You can.
Yes. All right, are you guys able to see my screen?
Yes, sir. Yes, sir.
Okay. All right, so
This meeting is being recorded.
good morning from Texas and good evening to you all in India. As Swami just pointed out, I will be teaching a part of this course on machine learning as applied to geosciences, even though it's called machine learning and geosciences, and our discussions are going to be fairly generic in the sense that you can take these tools and apply it to your own field of specialization. Actually, I've been teaching this course at my university, and I've actually taught it twice, and this will be offered again next year. And like ISM at UT Austin also, majority of the students signing up for my courses are from outside of the department. So I try to keep this somewhat general discussion, but for the geoscience students, they can apply these tools to their own problems, and people from other fields of engineering, they can apply to their own applications. So here is the content of the introductory lecture that I'll cover today and tomorrow. So first of all, I'd like to go over course logistics, okay, and the motivation behind studying this particular subject. Now, one thing I wanted to tell you right away is that actually machine learning is not new as far as the geoscientists are concerned. We have been using techniques such as inverse theory and geostatistics, and these are building blocks. In fact, you will see a lot of similarities between what is done in machine learning and what is done in, say, seismic or geophysical inversion and geostatistics. And I'll try to tie up these fields towards the end of this course. But at the beginning, I'll just very briefly give you an overview of what we do in geosciences, and then what is it that we can do even more using the new tools. So very first thing that we need to understand are what are the basic questions in sciences and similarly in geosciences, and how do you go about trying to answer those? And what you immediately recognize is that actually what we do is no different from what is known as interpolation, okay? Basically, we like to interpolate our data given some sparse set of observations. And for interpolation, we use different tools. Like, in inverse theory, we use physics-based inversion. In geostatistics, we use spatial statistics. And in machine learning, we do slightly different things, and then we'll talk about those. So we have different methods for answering some of these questions, physics-based, statistical, and so on. So the thing that you immediately ask yourself is, so what is new now? Is it just a hype that everybody's talking about machine learning, or are we able to actually do something different from what we have been doing? So big thing that you see is this idea of automation. That means a lot of these tasks that we do can be done in an automated manner without having to provide your input for each set of new data set. And the other thing is that we are able to we're able to mine huge amount of data sets, and that has made a tremendous change in terms of what we can actually see. And of course, the very first thing that we want to talk about is how do we learn to learn? And this is a human experience. We're trying to teach a machine to learn some of the tasks that we are able to do on a routine basis. But do we really understand how we learn to learn? And then we talk about what is machine learning, what are the different kinds of machine learning algorithms. And the most important part is that how do we learn under uncertainty? So we can take your real life example and see that whenever you're trying to make a decision based on certain set of observations, that the observations are always associated with some degree of uncertainty. So given that, how certain you are about the inference that you're going to make. All right, a little bit about course logistics. First of all, I want to be quite frank, and I will tell you that I'm not going to encourage any kind of plagiarism. No copying. Whenever we have exam, we know how to catch if anybody plagiarizes. And if you are caught plagiarizing, you'll be basically penalized. You'll report to the highest authorities. And this is something, don't think it's fun to copy other friends' homeworks. Well, the name of this course is Artificial Intelligence and Machine Learning. And the course number here. The plan is for us to meet Tuesdays and Thursdays, Tuesday and Wednesday, or Thursday, I don't know, whatever. Yeah, I think it's Thursday, right, Shoman?
Thursday, Tuesday and Friday it is from 5 to 5:50, and Thursday is 6 to 6:50.
Okay, so Thursday is 6 to 6:50. Okay, I'll correct my notes. All right, now we'll be making use of a website where I'll be posting the notes and slides in Piazza. And in fact, someone has sent out invite to all of you to register in Piazza. And in fact, every lecture, what I'll do is for my lectures, I'll try to post my slides and maybe a day before the lecture so that if you want, you can download and come prepared to the class. For example, you can find today's lecture already posted in Piazza. And this is a general link. However, you can click on it and you can actually go to that site if you like. But otherwise, I think if you go and register yourself, everything is going to be accessible to you. So I'll be teaching this course, co-teaching it with Somen. The way we plan is that I will cover one half of the course and Somen will cover the remaining half. And I'll tell you how we're going to split it. It does not mean that I'll continuously lecture for some time and then someone will come back. Someone will come, but there is a split in terms of the topics. Okay, so roughly, I'll try to have one topic lecture and one exercise every week. When I say exercise, this is basically means some kind of computer exercise where we'll give you some data and some pieces of codes, and you'll be expected to run those and teach yourself how the algorithm works, and then come up with your own queries if they don't work, or what is it that you can do to improve it further. And we will assign group homework, and roughly once in 2 weeks. It could be different, but roughly on an average once in 2 weeks. Since we have many students registered for this class, I don't know what is the final number. Someone was telling me more like 65 now, or maybe.
And now it is 67, and then there is a queue of the 17, which is 15 to 17, which is registered under GPD. If they shift, then it will increase.
Okay, so homework can be done in groups. So you can form your own groups by the end of this week and let us know. You can let Somen know, and then we will basically expect that each group will submit the assignment to us, and everybody in that group will get credit. So even though, Yeah, but don't copy from other groups' homework and things like that. Already we're giving you enough freedom to talk to each other. So it'll be nice if everybody participates. Even though it's a group homework, if you really want to learn the subject, you have to do it on your own. There'll be some midterm exams, and this is something that someone can tell you better because I'm not familiar with the system that is followed in ISM. All right. What I would like you all to do is something called a capstone project. So again, the same group that you have right in the beginning, maybe a group of 10 students, because there are about 70 students, so 7 groups would be easy to handle. And then in the capstone project, I'd like you to pick a project in your own field, and you are free to discuss your project ideas either via email or in one of the classes with me or with me and Soman, and we can sort of guide you, but we're not going to hold your hand and tell you this is what you should do. And normally I like my students to make a short presentation on project ideas. I'm not sure if this is going to be feasible, but if it's not possible to have presentations from you, we'd like to see a short write-up on the project ideas after 3 weeks of class. And then at the end of the semester, I expect each group to submit a final project report and a workflow in Jupyter Notebook. Okay, so if you don't know how to program, don't worry. The programming is really not difficult. All it matters is how well you can formulate the problem and what are the different steps. So Python is actually a pretty slick programming language, not necessarily the most efficient, but it's very easy to merge together different parts. And I'll be giving you different codes for different assignments, so you'll be able to work with those and then learn how to program also. So familiarity with Python, Jupyter Notebook, Google Colab, LaTeX, and MATLAB would be helpful for this class. But if you don't know, not yet programmed in any of these languages, don't worry. Google Colab is a facility where you can actually run your machine learning codes without installing any of the packages yourself through the website that Google has put together for research collaboration. And for small problems, it's easy to run any of these codes. But if you want to run big jobs, then you'll have to pay for it. But otherwise, it's generally. But most of the projects that you will do in the class, they are small ones. So either you run it in Google Colab or download the package yourself. Okay. So here I have given you some of the resources. You can click on these links and you can see some of these notes. And for all of these, I think the one I actually myself liked a lot is this book by Bishop, Pattern Recognition and Machine Learning, and the book by Murphy. And these are, Murphy is more statistical approach to machine learning, and I think you're going to like this. And there's this book by Charu Agarwal, and that's actually focused on deep learning methods. And lots of resources available online, and you can probably next time and tell us as to what your favorite choice is. So here, also there is a link to a particular book. It's Introduction to Machine Learning with Python. So I would encourage you guys to look into this, especially those who are not familiar with Python. All right, so what is the objective, or like what are the learning outcomes? What I expect the students to finally learn out of this course is to understand how various machine learning algorithms work and how to formulate your own machine learning application. And this you can demonstrate through your capstone project. Implement on your own and come up with some novel ideas for improving. Identify algorithms that are appropriate for a particular application, and most importantly, get motivated to learn more. So this is an intro class, and this field is rapidly expanding. Every day there is new development. So the main thing is that once you understand the basics, that will get you motivated into digging into more details of some of the new developments. Yes, machine learning uses calculus, linear algebra, optimization, statistics, and you guys are from the best school, one of the best schools in India. So I don't think you need to be afraid of that. If you have not been exposed to any of these subjects, I'm sure you can learn more. And they are actually very basic calculus and linear algebra that we use. And optimization, you may not be familiar with, but I'll try to give a lecture and also give you some codes on that. Okay, so the general plan is we'll have a lecture, and then we have some lab. Okay, so I will do the introduction, then there'll be a lab on introduction to Python. So I'll give you some Python codes to work on, and then Python libraries. So you have the list, because I have actually uploaded this whole PDF file. The only thing is that we may not follow exactly the same sequence, but we'll try to cover as many of these topics as we can as we go along. You can look at this list at your leisure. So the first thing that we need to look at is scientific thinking or scientific method in research. And this is something that is used in all fields of science, right from biology to physics and chemistry. The scientific methods allow researchers and scientists to test their theories in a standard manner that is uniform to everyone globally. This is very important, is to be able to test your hypothesis or theory in a standard manner. Now, one of the main advantages of scientific method is repeatability. Okay, since the experiment and all the details are expected to be recorded clearly, it allows others the ability to replicate the experiment and accept the hypothesis widely. Now, not exactly from the same idea, but nowadays we are mostly following open source. And this is open source policy. What it means is that whenever you come up with a new technique and you write an algorithm with some data set, we try to make those available worldwide. So anybody who's interested in it actually can download and first, number one, repeat what you did. And number two is basically make some improvement and then post it back for others to take advantage of. So this way, the scientific progress becomes very rapid. So scientific thinking involves, first of all, asking a question. That means identifying the problem and then find out what information is unknown or missing. Okay. Then you research on what is already known and what isn't. This is very important. Okay, so that you don't reinvent something that has already been invented. Hypothesis, prediction or an educated guess of a possible outcome. Then you test your hypothesis, you make some observation, you get some result, and then conclude. And then you communicate your results and date it through various media using a lab report. And one of the things that I wanted to point out here, this is how scientific thinking progresses. And this is how you should be writing a technical paper or report, okay? Talk about the question, talk about the research, talk about hypothesis, talk about your experiment, talk about your observation, and then you talk about conclusion. And oftentimes, I edit like 3 different journals, and oftentimes I see people writing papers where things are out of order and get mixed up. It's not so much a problem that people have language issues. The problem is a systematic way of presentation of your scientific thinking when you're writing a report. Okay. Well, about this, I came across this fantastic quote by one of the scientists who I admire the most. This is Richard Feynman. And he says that in general, we look for a new law by the following process. So first we guess it, then we compute the consequences of the guess to see what would be implied if the law that we guessed is right. And then we compare the results of the computation to nature. And if they don't match, then I basically modify my theory and repeat this. So this is the simple statement that is the key to doing science. So essentially what Feynman said is that this involves 3 steps: guess, compute, and compare. And you'll see all throughout that this is what we do when we say use inverse theory, or we use geostat or machine learning. Okay, guess, compute, and compare. Now there are 4 paradigms of scientific development, and the first paradigm started with experimentations, and this began in ancient Greece and China. Well, people tried to explain their observation through natural laws. Then came theory, when say scientists like Isaac Newton, they tried to make prediction and would verify their hypothesis by conducting some experiments. Then came the era of computation and simulation, where we started using high-performance computers in 20th century to explore regimes that were inaccessible to experiment. And then the 4th paradigm is data mining. So using more powerful computers, and the scientists begin with the data and direct programs to mine enormous databases for relationship. In other words, we like the computers to discover the rules by studying the data. And it's called data-intense discovery. And this is basically our 4th paradigm, which basically is the use of technology to do high-performance science. Okay. Now let's look at some geoscience application very quickly, just to show you a very simple example, and to mention and to show you like what are the fundamental issues. Let's say that we're interested in understanding what the subsurface rock layers look like. From the surface measurements, you can see some exposure, but that only gives you information about surfaces. But then what's happening inside the earth? So what we do is we can drill. So for example, these green bars, these are the boreholes. And in these boreholes, we can identify certain rock types. But then what's happening in between? We are not, we can't really go on digging holes everywhere, because first of all, this is not cheap, and this is really not encouraged, because you don't want to destroy the whole environment. Now, what we do is instead we make some indirect measurements, such as do some geophysical survey. In this case, it's electrical resistivity survey, and we come up with something called conductance or resistance or conductivity. So then we relate our conductivity to rock types in the boreholes, and then using this information, the what we call hard data in the boreholes, we can basically infer what are the rock types in between the wells and away from the wells. Okay. So this involves integrating data of different types and of different scales. Okay, because borehole data is very high resolution in depth, but very poor resolution laterally. On the other hand, our geophysical data, they do not have as much of depth resolution, but they are laterally extent. So then we can basically combine these to come up with some information about the subsurface variation. Now this slide basically should motivate you as to why we need lots and lots of data, and why we need to navigate through the data in a quick way. So let's say that we have some data, and these are shown by some blue dots and red dots. And this is geological data, but it could be any other data types, doesn't matter. And these red dots identify certain features in the subsurface. It's called buried valley. Okay. Now, given this this map, let's say that somebody asks you, can you come up with different zones of blue and red dots? Okay. So what is the most logical thing to do? Well, looking at the distribution, you would draw these lines, right? And say, okay, yeah, that looks pretty good. This is a possible conclusion. But then it's given to some other person, and he draws these lines. Okay. Now, you can say that this is way too complicated compared to the first one, but there's no way you can say that this is wrong. So which is the most likely one? You don't know. Well, one way of verifying this is to collect more data. So in this case, drill more holes. And if you did that, then you see that actually, even though the second conclusion looked unrealistic, when more data sets become available, now we have pretty good separation. There are two things that you realize here. One is that we have a need for collecting more data. And number two is classifying these data sets into different categories. And we'd like to be able to do this in an automated manner. And that's one of the objectives of machine learning or any other algorithm that we use. But typically, this is commonly used by machine learning these days. And we'll talk about those. So in seismology, we have earthquake data sets that are recorded in stations worldwide. And using those, we prepare seismic velocity distribution to show you what the interior of the earth looks like. And this is another picture which shows you, different parts, different zooms cut. And these are some of the recent techniques. But how did we achieve this? And that's something I'll talk about in a second. And here is another example of Texas data, oil production data. So here we have these dots that these show different wells. And here we have some gas wells, some oil wells, and so on, in different parts of Texas. Now, you want to come up with some zones where you have different kinds of discoveries. And how do we do that? We'll look into that in this class also. Let's say that I have a well log, and here the well is giving you some lithophases or lithologies. These are different rock types. But then how are they distributed? Okay, and let's see how we came up with a 3D distribution of different zones using different wells, but using some kind of interpolation in between. Okay. Here is data from weather forecast. For those people who, anybody is from atmospheric sciences, would be very interested in this, because nowadays you can see that, every hour, every minute, we can make a forecast of what the weather is going to look like. So here, the data is different. Here is done through some principles of physics supplemented by a variety of statistical and empirical techniques. So the kind of data set they collect include temperature, humidity, and wind. And then they use their understanding of atmospheric processes to determine how the atmosphere evolves in the future. I made a very important statement here, is that this is done using a combination of principles of physics and data science. So what they do here is make sure that we just don't do simple interpolation, but we also understand how the atmosphere behaves with changes in pressure, temperature, humidity, okay? And they use different kinds of instruments for that. Here is an example which may look like a completely different applications. We have different handwritings, like my alarm clock did not wake me up this morning. If this is typed, then you can basically read it very well. But then if somebody is writing it, I mean, our human eyes can identify those and read most of these unless somebody has a really bad handwriting. But then nowadays, actually, you see that the computers are able to read from your handwritten notes. So how do we do that? That's one other thing that we will look into. Okay, because for all of our applications, you see the data comes in different forms. Some are digital, some are analog, some are handwritten notes, and so on and so forth. How do we integrate all of those to come up with a conclusion that is realistic and meaningful? Facial recognition. We have faces of different people, and you can see that if you have a smartphone and if you have some pictures in there, especially an iPhone, you can actually see it. You can identify the faces of different people. Now, only the other day, actually, on my iPhone, it came up with a group picture of faces from my family members. I never told who the family members are, but it came up with those faces. So how does it recognize those? So some of these ideas are sort of maybe outside of your own field right now, but then you see that these ideas are also important. Same ideas can be used, for example, to discriminate between different structures in the subsurface. And same thing can be applied to other applications, other fields, okay? And this facial recognition and image processing has taken quantum leaps, in terms of using machine learning applications. Speech recognition is one other area. You can actually see that there are some translators. People are speaking in different languages and they can get translated. Self-driving cars, and there's a lot of research going on. So you have all of these cars here that are being driven, and a human being can make decisions very, very quickly. So can we actually teach a computer how to make these decisions? So here is a car, and it's safe to basically speed up a little bit and then go in front of this car. But how does a car or how does a computer know it? Still, is a bit of an issue. It's not there foolproof. So first approach that we take is called physics-based. This is what we geophysicists do. And this is called inversion. So we actually put some data and we put our understanding of physics as to how we explain the data, and then we run inversion. And that gives us result and tells us about what are the parameters that actually cause the variations that we see in the data. Now, this is not just in geophysics, it's used almost in every field, engineering and sciences alike. So the way it works is that you start with a guess answer, then you run your physics-based modeler, and then you generate data on computer. And you compare against observation, and you compare these two. If they match, then you say that you found an answer. If they don't match, then you update your model. And then you rerun forward modeling and repeat this loop until you get a match between observed data and synthetic data. Now here, one important thing is to find what is known as an optimal model, a model that can explain your observation, okay? And this is done using different methods of optimization. And I will explain those to you because those are some things that are going to be used even in machine learning. Okay, so I already talked about this. Okay, so one important thing is how do we represent our data? All right, so these are all digital data. So you can write those data as simple floating point and integer numbers and concatenate those in a long vector. Okay. So for example, in a borehole, you have some measurements, or you make some pictures, and then in the picture you have some pixels, and each pixel has certain code for a color. Okay. So you take those and put them in a long vector. Okay. And that forms our observation. And this is our unknown. This is our set of unknowns. And again, we put those in terms of put those in a long vector. And the idea here is to be able to relate this to that. And you should note that number of observations is never equal to the number of parameters that you are interested in searching. And this is our physics, is that given a particular M, from your assumption, can we predict what the data looks like? And this is done through an operator G. And typically this is a partial differential operator. But you can, in some cases, you can simplify it, give it a linear form, and this becomes a matrix. Okay. So now, given this equation, we have to go backward and find out what M looks like, and that is what inverse theory does. And the way it's done is we try to minimize the difference between observed data and synthetic data. And this is a notation for what is known as norm. And the norm is simply the distance between 2 points in a multidimensional vector space. So here, D is the data space and M is the model space. But GM is again into data space. So we just look at the difference between the 2 points. There are many ways of measuring this. And the simple Euclidean distance is the L2 norm. And here we have this observed data minus synthetic data square, and then take the average of these, okay, and sum an average. So that measures the distance between these two. So what is the objective here? The objective here is to minimize this such that your observed data, it comes very close to synthetic data, okay? Okay, I think, so this is an example of ultrasound scanning and sonography. And this is basically using the same technique, physics-based inversion. These acoustic waves. These are the PET images, positron emission tomography. This is pre-chemotherapy, post-chemotherapy, 2 months and 4 months. And here you can see the change in the image. Again, we used a physics-based approach to come up with these images. Similarly, these are the time-lapse images, 2 time-lapse images from seismic data. And here we can identify how the oil has been pushed from the injection well to the producing well. Okay, and again, the ideas are very, very similar as what you saw in ultrasound. Okay, this can also be done in a statistical fashion, but I will not go into details of this today. So in Geostat, like an inversion uses physics-based. Geostat is the application of several statistical tools to determine spatial distribution of geological variables. They make use of variogram, creaking, creaking, and so on. So essentially, looking at the data distribution, we come up with a statistical model. So here, I will not go into glorious detail, but here is an example of kriging. So the difference between standard interpolation and kriging is that it actually picks up the spatial relationship. So for example, there are 2 different kinds of data types given by the shades here. So if you want to interpolate and come up with what is the value at this point, which is not known to you, and this is the known answer, let's say that given these open circles, here also you're expected to predict what this looks like. If you did a simple distance-based interpolation, then you will be assigning this property to that point. However, that is not correct. So if you use some spatial relationship, then you will be using these points. So this is what is done in Geostat, and there's a method called kriging, and you can also use multiple data sets for kriging. All right, so these are some examples of clicking. You can look at that. So the next step would be like, what is it that you can do beyond physics and geostatistics? Do they have limitations? Can we not combine these two? And it turns out that you can look into machine learning. You can understand machine learning also from the perspective of physics and geostat. Even though machine learning scientists or the engineers, they tend to ignore what has been done in geosciences, but we geophysicists and geoscientists can very easily relate our ideas to this. And I know there are students from other departments here, and you will also benefit from learning a little bit on inverse theory and geostat. So you'll see that the machine learning is not completely different, and we'll explain to you what the differences are and what the similarities are. And the good news is that you have big data, large memory, and we have computation time, but the computers are very fast and big, so we are able to do a good job with a lot of data sets. Finally, what I would like you all to do is to download these lectures, and then in the last page, I've given you instructions for installing Anaconda, which is basically a set of Python libraries used in machine learning. And I'm sure some of you have already access to this, and those who don't, please look through this list and then download and just try some simple coding before we come to class next time. And of course, I'll lecture next time, and then after that, we'll give you some practice session. Okay, and this is how your installation instructions. Should have no problem in installing. And the thing is that this is all open source, and this is basically platform independent. So it doesn't matter whether you're using Windows PC or using Mac or Linux, it'll work everywhere. There is a version of it, and you should be able to run those. So with this, I'd like to conclude today's lecture, and we have only a couple of minutes, so we can take some questions or comment. Just unmute yourself and ask me a question. I don't know if there is anything in the chat. No. Any question, comment?
Sir, how can we differentiate between geostatistics and the statistics that we learn in maths? Means how they are related and how different they are?
They are actually, I wouldn't say that they are very different. The term geostatistics was coined because this was applied to geoscience problem where they capture the spatial statistics to be able to make inferences, which is not so common in the general statistics application. Okay.
Thank you, sir.
Yes. Yeah. I thought, I don't know how many students came into this 48. So how many are registered? And let's decide that based on the full strength of the class, because this is, I think there was some confusion as to who all can register this. If it's close to 80, then I would say that make a group of 10 students. And if it's 50, then I would say a group of 5 students would be okay. Okay. And one other thing I'd like to tell you is that try to mix the members of the group. For example, you should have students from different disciplines in a particular group so that you can interact with each other. And that is one thing I'd like to be able to see in your groups. So that way it actually goes much faster. That's what I've seen in my own teaching here. Okay.
Excuse me, sir. This is Prashant from Geoexploration.
Yes.
Sir, actually, there was some confusion regarding our class. So the people from my batch could not attend this for first half an hour. So we don't have the basic details that what is this formation of groups and also can we get the recording of this lecture or the basic summary of the lecture?
I think Soman is recording it, right? So he can make it available. Yeah.
Okay. Sir.
Yes, it is possible.
Okay, sir, please share it with us. It will be very
But this is only for today, because we're not gonna let you have the lectures recorded every day.
sir,
Then
obviously,
you'll
sir.
stop coming to class. Okay.
Yes, sir.
Yeah, only first week lectures would be available online, and then I think at the end of the course we can make those available, but we're not going to make those available every day. Okay.
Okay.
All right. Anything else? Okay. So then I'll see you in the next class. Okay. Bye.
Thank you, sir.
Thank you, sir.
Thank you.